Yeah, I thought I stored it in bookmarks, but I didn't. I had to look it up again. So, yeah, fine. Something to get you going in the morning. Anyone done anyone a wingsuit pilot here? Me neither. Very wise. Quite amazing, really. Yeah. So, so it seems that we've got through to now with very few hurricanes. Usually we can find a hurricane on the news homepage that I use, but it's been a very hurricane-free year here. I guess there was a big typhoon that ended up in Alaska, in the Pacific, from the Pacific, but on the East Coast we've had really nothing. So we usually get something. So we'll talk a little bit about, carry on talking about fluid mechanics today, and in week 12 we'll talk about external flows, the kinds of flows that would affect a turbine blade, for instance, but also affect this, and this is related to the kinds of things we've been talking about in terms of Bernoulli's equation that we'll kind of round out today. We were talking about conservation of mass, week 6. Week 7 was conservation of momentum, and this is conservation of energy this week. And so all that allows us to do, as you've seen, is we can take Bernoulli with fluid losses. And so in dealing with real problems, we have to be able to deal with that. So that's kind of what we'll chat about when we get going today. It's dark. He was going to fly down Everest. I'm not sure he ever did. This is from 24, I think. So I'm not sure if he's still with us or whether he reached his goal of what he wanted to do. Anyway, so. Well, we looked at these things last time, but maybe this is worthwhile watching again. And so what we'll talk about today is we'll move on from where we left off last time. We kind of ended up collapsing things down to porous media flows. So let's start from there today, and then we'll expand to external flows, kind of to get a big picture feel for how this course maybe fits into your overall program. I'm not sure that you'd use fluid mechanics every day, but if you're a reservoir engineer or groundwater hydrologist or a geothermal engineer, you certainly would use some very specific aspect of it every day, looking at how to pull contaminants out of the ground, how to clean up after underground storage tanks have leaked, getting shale gas out of the ground, or hot fluids out of the ground as well. So that's kind of where we go. So we made the point last time that we can look at porous media flows. This is, I guess, a kind of a marriage between the two. This is a porous media flow because you're looking at flow within tubes or conduits within the subsurface, but for those flows, we're actually they're solving for the inertia of those flows as kind of a free body problem. So we'll try and stitch together the idea of porous media flows, which is shown here, and we'll try and put that in the context of external flows. I should stop blabbing on about and get to it. Anything to chat about before we get rolling? Don't forget, next week is midterms week. Well, I guess you're in the second part of your marathon now, right? We're past the midpoint of the semester. You know what's planned. Should have looked at the review materials. The review materials have been online for a little time. And so I won't tell you how to prepare for it, but I think you perhaps have some ideas yourselves from your successful career so far, and you certainly have some background. You could certainly make some educated guesses about what might be on there. So, yeah, Nicholas. Yes, yeah.
So for everything that we've been going through, the internal flow would be like basically it's moving within a pipe frame. So within like a pipe like that. So then external flow would be like more akin to like waves hitting like flotsam.
No, it would be taking that same pipe, welding off the ends, and having airflow past it on the outside. Or a turbine blade, airflow over a turbine blade, or over an aircraft wing. So that would also be a single fluid. It could be a liquid or or gas, air in the case of a wing, or water in the case of a hydroplane, right? America's Cup boats sitting on those hydroplanes on their keels. And so, but the main issue is that, actually we'll talk about it first, is that when we've talked about porous media flows, we derive those equations directly from conservation of mass only, not conservation of momentum, which is Bernoulli. And so they implicitly ignore the inertia term. And that's just fine for porous media flows because they're slow. But if you have large velocity flows, the essence of the problem is the inertia term. So that's it. Well, good question to start us off. So what I want to do today, I'm going to try putting this thing on the side. We talked about differential analysis kind of Wednesday. I didn't realize you had a test straight after this on Wednesday, right? I meant in thermo? Yeah. So I met Nelson on my way across campus. So we've kind of talked about this already. We'll talk about flow nets. In 452, have you talked about flow nets? No? Yes? Curvilinear right angles. Okay, so we'll talk about that. And we'll talk about some kind of standard solutions for flow in a pipe and flow between plates. So we'll go as we can get on. So, what do we have? The last thing we talked about was this. And so you will remember that this equation here is part of our conservation of mass relation. And we derived, instead of writing it in this form, we could write it as a sum of three differential components. And that's convenient for the kinds of problems we solve, because I'll get back to this again, because if we look at flow in porous media, we can define this behavior as, for a pressure gradient, this is dP, this is dx, and I suppose this could be z. This would be z2 and z1 in our parlance, right? And of course the z-axis is positive upwards. And so we can write two forms of Darcy's law, which just say that the velocity that something comes out of this system is equal to minus hydraulic conductivity times the gradient of head. Or we can write it that velocity is equal to permeability divided by viscosity and the pressure gradient with length. So this term here this would be head, right? It's the sum of elevation plus pressure. And so we can write Bernoulli's equation as P over gamma plus elevation plus V squared over 2G. We'll call that hydraulic head. We'll throw away this term because you don't want to deal with it. And for each of these expressions, they're the same. They're just, I should write the individual components. K is equal to hydraulic conductivity. And it's in units of meters per second of velocity, because this is length over length, it has to be. K is what's called permeability. It's in strange units, meters squared. Viscosity, we know, it's no different from our other terminologies that we've used. And you know it's in Pascal seconds. water is 10 to the minus 3 Pascal seconds. What else? Everything else is the same, so I guess those are the only two terms. And what we did was we merely substitute this into here for velocity, or this in here for velocity, and we ended up with two expressions coming out of it. Whoops. One for hydrologists, which would be something like specific storage times the change in head with time is equal to hydraulic conductivity d2h dx squared. So when you substitute dh dx into here and differentiate it outside, it just becomes a nested differentiation. And SS is equal to specific storage. Specific storage. And if you're a petroleum engineer, it'd be something like this. dP dt, same format, is equal to this from this expression here. d2p dx squared. So you'll see those throughout your career. Beta was compressibility. Which is in units of 1 over pascals, 1 over stress, and N is porosity. So, which is defined as the volume of void space, voids, divided by the volume of total volume. So in other words, if you have a piece of porous media that looks like this, the total volume is VT on the bottom there, and it would have some grains in it which would take up the space, and the void volumes would be the intervening part. So if porosity of 1 is no grains, porosity of 0 is no voids. Typically, porosities are of the order of 0.2 or something like that. 20% of the space is voids. So writing's not great, but the point is, and to come back to the first point, was that this is derived purely from conservation of mass, nothing else. The viscous head loss, which we have in Bernoulli's equation. So you remember that when we write Bernoulli's equation in longhand, it's something like upstream pressures plus velocities plus energy put into the system is equal to downstream. I won't write out those same terms, but it's also plus the sum of head losses. So this is just Z2 P over gamma 2 V squared over 2G for velocity 2. This loss term is put into our system in some way to take care of the viscous resistance. So that is taken care of in this term, right? If you have a velocity coming in here and coming out the bottom, if the cross section doesn't change, then, and it's at the same elevation, then the pressures upstream and downstream should be the same. If they're not the same, the only reason can be because this is finite, and this is what's represented in hydraulic conductivity and permeability. They just define how much frictional drag there is on the particles as it goes through the conduit, which is the through-going flow path. So that's that. And so the other thing that we'll do is that we'll now realize that units of this, I didn't talk about specific storage, I think it's the units of 1 over time, which is strange, right? But you could tell that, right? If you just rearranged this expression, you could rewrite it as specific storage is equal to dt over dh k dx h over dx. And you know how to get rid of these. These have the same units. This is meters per second. This is meters. And this is time, which is seconds. Actually has no units, right, in this particular form. So length over time, am I doing that right? These are definitely no units. Have I missed a term? Yes, I have. Squared. So this is units of 1 over m. So yes, right, it's not time. So this cancels out here. This cancels out here. And so it's units of 1 over m, right? This squared term on the bottom has to be accommodated here. So the units of this are not 1 over s. They're equal to 1 over meters. And I guess what that is saying is if the hydraulic head goes down by 1 meter, it squeezes a certain amount of volume per unit volume into the adjacent elements. That's the physical meaning of that. So the utility of looking at these expressions is that we only did this is in 1 dimension, but of course you can substitute this for velocity in the y direction is equal to k dh dy. So you'd end up with multiple terms. So in 2 dimensions, you'd end up with, take the first one, specific storage dh dt is equal to hydraulic conductivity in the x direction, d2h dx squared, plus hydraulic conductivity in the y direction, d2h dy squared. Oh, and by the way, we've used these 2 terms of hydraulic conductivity and permeability separately, specifically done uppercase and lowercase. They're related as hydraulic conductivity over viscosity is equal to, permeability over viscosity is equal to hydraulic conductivity over density times gravitational acceleration. This is water density. So they're related, they're not independent of each other. So if we look at 2D and we look at steady state, then what we could do, if we look at steady state, then there's no change in head with time. And if we look at the case where the hydraulic conductivities are the same in the x and the y direction, then this expression just reduces to d2h dx squared plus d2, bless you, dy squared equals 0. And so h is referred to as a potential. In our case, it equals pressure over unit weight plus elevation. But what we can do is with this second order PDE, it's actually quite a useful equation, because if we do wingsuit man, we can define relative to this expression here, don't know why it doesn't want to do this, actually a bit like what we've already done. If we define some streamlines, so just like stream tubes in Bernoulli, we're just doing nothing that's different. It turns out that this equation defines kind of a lattice, if you like, of streamlines which are orthogonal to each other. Streamlines and potentials that are orthogonal to each other. So I'll try and draw this. And that network, that flow network, which is suitable actually to work in the air around someone, but also in porous media, where the porous media is kind of homogeneous with fluid going through the interstices. is that this defines streamlines and equipotentials. And on each equipotential, H is constant. So this is our potential that we're looking at. And so long as you can draw this network with two provisos. So this is a flow, not follow, flow net, or yeah, let's call it that. Two requirements. Brandon, do you remember from Byron, not Brandon, two requirements. One is the cells are equiaxed. Fancy name for square. So in other words, this dimension and this dimension are the same. And intersections orthogonal. So in other words, these angles here need to be right angles. I won't go through the math of why this is the case to satisfy this equation. I'm not sure it's useful to us. We just need to know that it kind of works. And so the bottom line is, if you want to solve the flow equations, then you need to be able to draw a flow net that satisfies these requirements. That's all it needs to satisfy. And to try and make an easy example, use one of a sheet pile wall. So don't see much big construction in State College, but in the big city, when you excavate basements for buildings, put a retaining wall up, and you start off with maybe a water table. So it's twofold. One is you want to be able to keep the water from flowing into it, so you push this into the ground. And one, you want to stop it all collapsing into the void. But you might expect that you would have a water table set itself up at the bottom of this pit. And relative to this, you can define some kind of datum. Z equals 0. And we were saying that if you can draw a network which satisfies the requirement of this, then let's try doing that. Something like this. These would be our streamlines, and there'd be another one outside that. I'm not sure if we're going to use all of these. That's not a good one. And I want to be able to draw a line through them. So this is satisfying this. That is satisfying this. I guess the other thing that we're also satisfying is that this length and this length are roughly the same as each other. And I would just go on to draw these. Some of them might not be such great squares. Fine. Not very good. Maybe I do better on a piece of paper. And so the idea is this. If you take one of these components, and I draw it out like this, it's also equiaxed. and I look at flow out of this. Has to be the same going in as out. This is a streamline. H is equal to H1. H is equal to H2. This is a streamline. This is a streamline, right? It's confining flow. And I can define this as a length dl. And I can find this as a width dw. And I can just write Darcy's law. As velocity is equal to hydraulic conductivity times dh dx. I can also write this as a volumetric flow rate, Q. Q would be equal to multiplying both sides by an area. And this area, I suppose, is equal to dW. This together is Q. I suppose it would be in meters squared per second, right? It's meters per second in velocity times a length, really, plus 1 meter into the page. So we need to do that. And I could also write that dH is equal to H2 minus H1. Actually, H1 minus H2, isn't it? Same terminology as before, upstream to downstream. And I suppose this term here would be equal to dl. So the Q for one stream tube would be equal to hydraulic conductivity, width, dH over dl. We know that for all of our components, dW is equal to dl, right? We said that they have to be equiaxed. So this and this drop out. And this is just equal to hydraulic conductivity times dH. And dH is equal to H1 minus H2. But we also know that each of these drops, H1, H2, H3, H4, 5, 6, 7, 8, and 9 in my particular case. They're equipotentials. Each potential drop has to be the same. And so we can write it either as the individual head drop between this point and this point, H1 to H2, or we could also write it as H1 equal minus H2 is the same as H2 minus H3, right? Every time you go across one potential, you're losing the same amount of head, potential head. And we could also write this as H total, which we'll call delta H, divided by the number of drops. So the number of drops would be, you go from this one to 1, 2, 3, 4, 5, 6, 7, 8. So in our case, number of drops would be equal to 8, or in my particular case, whatever you have. And so we could substitute this in as equal to The flow in one stream tube is equal to the hydraulic conductivity times delta H total over number of drops. We're just substituting yeah, so H total is equal to delta H. I should probably, H individual is equal to delta H over ND. And I should remove this, right? Just modifying that. Better to be correct than pretty, perhaps, right? And so this is the flow rate for one stream tube. And so for Q total is equal to Q stream tube times number of stream tubes. Number of stream tubes is 1, 2, 3, and however many you'd have. And so the bottom line is Q total is equal to number of stream tubes, hydraulic conductivity, the total head drop across the system divided by the number of drops, ND. I'm falling off the end of the desk here. Yeah.
Does that say, next to the Q total, does that say QS times NS or NG?
Where? Here?
No, next to Q total on the other side.
NS
Okay.
and NS. Number of stream tubes, which is 3 in this particular case. So if you wanted to calculate for this particular example, the total flow rate out of the system is just going to be the number of stream tubes is 3. The number of drops is, it goes from 1 to 9, so it's actually 8 drops, right? 1, 2, 3, 4, 5, 6, 7, 8. Times the hydraulic conductivity, I don't know, 10 to the minus 4 meters a second, don't know, just a number, and delta H. And delta H in this particular case would be H1 minus H9. And what I mean by that is that H1 would be this length here. Doesn't matter where the datum is. You can choose it all the way to the center of the Earth. This would be H1. This would be H9. And so this, I guess, here would be H1 minus H9 equals delta H. Very simple. Incredibly simple way to do it. You can use it for flows around a wing, you can use it for porous media flows, but the bottom line is that the expression that defines that behavior is just this. So there's some description of this in my rather kludgy notes, but that's the straightforward interpretation of it. I guess the other thing that you know is that you could also calculate what the head is at any location in this just by subdividing each of these delta H's. And so you would be able to say that, I guess in this particular case, H3 is equal to H1 minus delta H, number of drops, which is 8, right? Which is 8. And the number of drops to get to that particular point. I guess we could call that number of drops to 0.3, right? So H1 would be this magnitude here. The total hydraulic drop over the system going from here to here would be this delta H. And if you went 2 eighths of the way to this point, then it would be 2/8, if you wanted to get that as well. So you can get lots of information from purely this graphical way of doing things. And all you have to do is to make sure that your squares are equiaxed, flow rate and across them, and that they meet at roughly 90 degrees. And you see there's some strange things going on here, but the rest of this, these aren't very good. Could have drawn it better, should have come deeper, I suppose. But if you can draw that, then you have a solution. So lots of math to get there. We avoided it. This is a more difficult example, but the same thing. But I guess I'll point out on this the idea that we define a head as being equal to the pressure head plus the elevation head. And so if you take this as a datum, you know that if you draw the changes in pressure with depth, you get this pressure prism. This was our week 3 stuff. So this is P equals unit weight times, I guess I'll call this H, not Z. But if you go up from here and draw a straight line, then at this point here, the pressure is a maximum, but the length of this axis, so I guess I'm just trying to make the point here, that this is equal to, this is Z, the elevation, and this is P over gamma W. And no matter where you go on this back surface, if the water table is sitting here, or the swimming pool height is swimming here, as you go deeper and deeper, you get more and more pressure in your ears, but your elevation diminishes as you go down to this point. So everywhere on this point has an equal hydraulic head. So this is an equipotential by definition on this back point. And the reason for that is that the sum of these two components adds to a constant in this particular case. And so this is the graphical representation of this. And this is just the same derivation that we went through, if you want to have it. Okay? So, useful thing to do. We avoided the math in getting there. But this is the reason why we can divide things in terms of this potential, which we use for flow nets. So now, let's go back and do something a bit more complex. So to remind you, we got these expressions for frictional losses in porous media by just writing conservation of mass. That's not the only thing that we've done. We've also used conservation of momentum. And if we have a bit of space here, we can write the expressions for this. So you'll remember that we wrote something like, for conservation of momentum, we had something that was sum of velocity times mass flow rate is equal to sum of forces, which of course is the same as Newton's first law, which is F equals ma. And we also made the point that this is kind of similar to forget that it's an equal sign. So we made the point that this is basically the same as Bernoulli. V squared over 2g term is the inertial acceleration term, which is what this is, and so this is what they are. So what we've intrinsically done when we did this and used potential to get this, we've intrinsically ignored the term which is v squared over 2g. And so that's probably okay for groundwater flow, probably okay for flows in air across wings, but it's not so good for the other things we might want to do. And so in the same way that we took a volume, a differential volume, for conservation of mass, and we looked at inflows and outflows into that volume. I'm not going to do anything other than label it dx, dy, and dz. You remember that we took flows into this just as velocities in and a velocity out, and we came up with this differential expression here, which we could use usefully. We can do exactly the same for the momentum equations. So we can write this cube, we can solve for flows into and out of it and the forces they'd apply. I won't do that, but I'll jump straight to the expressions that come out of it. Kind of complicated. I don't think we need to understand everything about them. But we could perhaps try and understand some things about them, in that our expression that we want is, I'll write it here, as sum of velocities times mass flow rates is equal to sum of forces. And that also breaks down for this expression. So this expression has come from looking at flows into the differential cube in the x, y, and z directions. So this is looking at summing mass times velocity in the x direction. This is from summing mass times velocity in the y direction, etc. And we can think about the terms that come out of it in terms of Bernoulli. So what's this? This term here actually looks just like dv dt times rho, which is the inertial term, right? This is a substantial derivative. Velocity with time, velocity with x, velocity with y, velocity with z. So this is just a substantial derivative. The terms on this leading diagonal, see if this works if I draw it like this way. Oh, I was hoping it would do an ellipse. But these terms on the leading diagonal are just the pressure terms. Oops, didn't mean to do that. This is, go down here. This is P over gamma. This is Z in Bernoulli. So Bernoulli have Z, we have P over gamma. We have these other off-diagonal terms are equivalent to the head loss, because we're going to account for the head loss. And this term is exactly the same as v squared over 2g. So that's all. So if we write conservation of momentum for a little differential cube, we get three equations for doing x, y, and z. We have four variables. Which are pressure, which is a scalar, and displacements, velocities, Vx, Vy, and Vz. And so we only have three equations, so we need another equation, and the other equation we need is just conservation of mass. Right, so we have four equations. So I'm not sure. So the bottom line is we can look at Bernoulli's equation in differential format, get super complicated system of equations. The equations have four variables in them, so you need four equations to solve them. So we can use these equations, which are called the Navier-Stokes equations. not that it really matters. Navier was a famous French mathematician. George Stokes was a famous fluid mechanician. And you get 4 equations for which you want to solve for 4 variables. We won't try doing that. These terms here are defined in terms of shear stresses. And we know that shear stresses we can define through Newton's law of viscosity as changes of velocity in the coordinate directions. This is Newton's law of viscosity. So things like these stresses can be defined in terms of viscosity and of velocity. So now we lose this term, which is the shear stress, because we can write it in terms of velocity, and that's one of our variables. These terms on the leading diagonals are just normal stresses acting at a point, and we know that px equals py equals pz at a point. So that's why we can write these as a single variable in terms of p. And so anyway, if we use that, we can write these expressions, and these are the final expressions. So again, 3 equations plus 1. We have 4 variables. We have velocity x, y, and z, and a pressure. And so this, again, is these equations written out just like Bernoulli. This is pressure head. This is elevation head. This is v squared over 2g. Sorry. Not. This is v squared over 2g. And this is head loss. So we could add these together if you like. So this is just Bernoulli's equation written in Cartesian coordinates, allowing you to solve for those questions that we solve of water coming out of a spigot and water washing over a lighthouse. We won't do anything as fancy as that, but we'll note that we can solve them for very specific geometries. And, yep.
Sorry, do you want?
No, go. No, ahead.
So just to be sure here, I feel like I'm getting lost in the letters a little bit. So basically, with the Navier-Stokes equations plus the continuity equation provides us with the system that we've been discussing for this lecture, and that's basically with these equations we can then use it to provide specific values that we want to look for.
These equations govern all flow around us, external flows, internal flows, accounting for inertial terms and for viscous losses around us. It's really just the same as Bernoulli's equation with the HL term in it, but it's generalized for 3-dimensional flows. And so if you take these equations and provide specific boundary conditions for particular flow geometries, then many of the terms go away and you can solve them to get closed form solutions for, say, flow in a pipe, which is what we'll look at now. Okay. Yeah, fine. Let's skip over, well, so this is the idea. So if you look at flow between 2 parallel plates, like a flow in a duct, the boundary conditions that you apply to this to get rid of those equations, I don't care about solving this, I'm not ever going to get examined on this, is that the velocity at the wall of this would be 0. And so v equals 0, vx equals 0 at these locations. Because of the symmetry, you might expect the maximum to be here in the middle. It would be, and you can solve the equations, and the bottom line is if you do that, you end up with some standard results. The standard result would be that the volumetric flow rate through that system. So the volumetric flow rate would be taking this velocity profile and integrating it. So if you want the volumetric flow rate, you can take the velocity in the x direction and integrate it with dy, right? So this would be a small length dy. And if you take every small slither that's dy tall and multiply it by the velocity that the fluid is going through that, then this is the definition of the flow rate. And so you can solve for the velocity, and then you can integrate it. And if you do that, then you get that the volumetric flow rate through a duct is equal to the height of the duct, 2b, the pressure gradient that is applied along that duct, dp dx. So it's equal to the height of the duct, the pressure gradient along the length of it, dp dx, and the viscosity. Standard result. So you get these equations. We've got it by finding out what the velocity is at every height in this duct, integrating it over each individual component. You get a complicated equation. It gives you the fact that the distribution of that velocity is equal to this. And that's exactly this velocity, right? So if you'd have in your duct the z coordinate, this is z equals 0. This is b, and this is b. Then exactly the velocity distribution you get would look like this. Maximum in the middle, 0 at the edge. So z is equal to 0. Sorry, z is equal to 0. The magnitude is b squared, so this is the maximum. When z is equal to plus or minus b, then this is equal to b squared minus b squared, and so it returns the velocities that we've solved for at the boundary. So it's a standard result. So that's perhaps useful, but maybe not. You could think of other things that are more useful. A much more useful one would be the idea of flow within a tube. And so the same deal. If you think of the walls of this pipe as being 0 velocity, then the velocity profile across that is given by the maximum velocity in the middle, 1 minus this ratio. R over R is equal to 0 in the middle. So this is equal to maximum. R over R is equal to R over R equals 1. 1 minus 1 is 0. And so the useful result that comes out of that is this, is that volumetric flow rate is equal to the diameter of the pipe to the power 4, viscosity, and the pressure gradient that's applied along it. Nothing more than that. And just one closing thought is that the one useful thing you could do with that, which maybe links together our Darcy flow behavior with our inertial behavior, which we've talked about at the end, is that you could do the ingrain experiment where you have a whole bunch of pipes in this. Each one of those pipes are equal to d in diameter, and you can actually calculate from this bundle of capillary tubes that the permeability of this is equal to the porosity times the diameter of the pipe squared divided by 32. So we use Darcy's law. So when we define Darcy's law as velocity is equal to permeability divided by viscosity dp dx. For the first part of our class, Darcy's law and conservation of mass describes flow in porous media. This describes conservation of momentum to get the flow in a single pipe. And we could use that information to be able to take the information for a single pipe. We have many of these pipes in here, put it all together, and you end up with an expression that you can throw back into Darcy's law because it's represented in these terms. And so kind of we've done full circle. If I come back to this, is that, I don't need to take it off the screen, but I have done, I guess, is that you could think of these blobs that are moving through this as moving in a single constant pipe, solving the inertial equations for acceleration, etc., in an open flow, just with zero velocity at the edge of the pipe. And if you sum all those individual components together, you'd get an equivalent permeability for it. That's exactly what's being done here. Just it's being done with a very sophisticated numerical model that discretizes this whole volume as maybe 10,000 little cubes, and looking at mass balance and momentum balance as flows go into or out of the other sides of those. And so that's it. So that's the linkage. So it brings it back hopefully to your majors in terms of what you might be looking at in the future. And I guess, we're not going to worry about these equations. The one thing that we'll use today, you use flow nets. I think it's quite a useful concept. But we'll also use the idea of flow in a single pipe. And when we talk about internal flows, we talk for 2 weeks about flows in pipes.